That's gorgeous.
Okay, so I'm going to go ahead and start, and this is great because this is an automated sparkler session. We each are going to get about 45 seconds to present our posters. Do you have a poster?
Yeah. Poster?
Did you give it to me?
No, was I supposed to?
Yes. Back in line. So to help us move along, if we are stuck talking about our beautiful, wonderful work, you are encouraged to applaud at the end of the 45 seconds. There will be 45 because we've got more. So speak 4/3 as fast. And it's now 4:15, so I'm going to start. And I am the first person, so I will be the model of probably failing at this. So we'll go for it. Okay. Okay, well, my name is Adam Bergasser, and I am a faculty member at UC San Diego, and my poster is on the Specs Prism Library. Who of you have used the Specs Prism Library? You are all wonderful, wonderful people. Thank you very much.
You are the wonderful one.
Well, thank you very much. So I wanted to share the updates that are coming up with the Specs Prism Library. We're going to be adding about 1,000 more Spectra to this library. And I have a group of students who are now working on developing a Python code specifically for this library. So you'll be able to access, analyze, and do all sorts of fun things with the Spectra using this Python code that we've already developed. And we're working actually with you guys, even though I don't know it, we are working with you. I also wanted to point out that we've been using this library not just for research, all sorts of research opportunities, but we've been using it for education. This is a great place for students. I'm off.
Hello, my name is Kelly Cruz. I'm an assistant faculty at Hunter College at City University of New York and a research associate at the Museum of Natural History. And my poster is on low gravity L-dwarf spectral templates. So what I've taken is optically classified low gravity L-dwarfs based on the Cruz 2009 system. And I think, let's see, for the L4s, there's like 4 to 10 objects in each spectral bin from L0 gamma, L2, and I shouldn't say gamma because I've included actually betas and gammas. So betas and gammas, they differentiate in the optical. I don't see in the near infrared so much, I can't distinguish very well between betas and gammas in the near infrared. Anyway, so I've averaged together all of those in the near infrared. Damn it.
Okay, this is an update on my studies of an L1 dwarf that happens to be in the original Kepler field of view. It has a variability of about 1.5% for the Kepler filter. You should think I-Z-band unless something weird's going on in the blue, and we can now rule that out actually from CCD photometry. It stayed the same for 2 years, so it's very different from what you see in the later brown dwarfs. Adam, please explain it for me, thank you. At Spitzer, 3.6 microns, we observed it, and it's in phase, and it does the same thing, slightly lower amplitude, but at 4.5 microns, it's not doing anything, right? This is flat. Some of you are playing bingo, so that you may be hoping that I'll say, what about magnetic fields? So I'll remind you that this has white light flares in it.
Hello, I'm Devin Hardgrillman from the University of Toledo. You guys all have been hearing about cool dwarfs, but we work on the coolest dwarfs. We're doing wide dwarf variability. We have a large Spitzer project. We've looked at 14 wide dwarfs in 2 epochs. So we have multi-channel observations. This is 3.6 microns and 4.5 on the right. And we have detected variability in wide dwarfs. 50% of wide dwarfs are variable at 4.5 microns. So we're up there with the L&T dwarfs for variability. So come check out my poster, number 209, and I'll talk more about wide dwarf variability.
My name is Ari Hines from Stony Brook University, and I have a poster number 205 on brown dwarfs, which are definitely variable, but not periodic. And you can see an excellent example here where, looking at it, you can see there's kind of a wiggle with a well-defined period there, but you certainly can't fit it with a periodic function. What we think is going on here is very rapid cloud changes. And this connects with some of the things that Avi and others have said today about brown dwarfs that you observe to be variable in one epoch. You re-observe them later, and they are not variable. You can see that this one, if you observed it for a couple of hours here, you would see variable or not variable later.
I'm Derek Homer from the Centre de Recherche de l'Astrophysique de Lyon in France. We are, among others, hosting the Phoenix Web Simulator, so I can't resist asking who has been using the Phoenix Web Simulator or models from that grid. So, big news number one from the poster is it's no longer a pure atmosphere model grid, but it's becoming a new version of the evolution and isochronic grid. We are about to release the part on M2L Dwarfs, since they are not particularly cloudy. I'm focusing here on the extension into the cloudy region. So we are having one cloud model covering all sorts of clouds, from the silicate clouds, and this is one of our extreme examples, the coolest.
I am Variability from the University of Arizona, and I present poster 236. As we heard in the previous session, we expect that brown dwarf atmospheres will have complicated 3D cloud structures, and these clouds will not only affect the signals we observe, but also the properties of the atmospheres themselves. Having thus a means to study the clouds and the properties and change, for example, their location and size, will help us get a better feeling for the physics and dynamics of cool atmospheres. With this in mind, we have created a Markov chain Monte Carlo code that can map the 2D structures of cool atmospheres. We have tested it against a Jupyter HST light curve and see it works and applied for the first time.
Hi, I am Elena Munjalakat from MPI in Heidelberg. So this is my poster, it's the number 272. And in this poster I am presenting an ongoing work about finding closed binaries using Exeter spectra. So we have 22 candidates, and we are using several methods like Burghaser indices and also comparing templates, including XSpecs. We are looking for the closed binaries, so you can go to my poster for further details, but so far we found 4 strong candidates with binaries. So thank you very much.
Marley, NASA Ames. You all have heard about disequilibrium chemistry. There's a long and winding road going from carbon monoxide to methane. Kevin Zonley, who knows more about methane than just about anybody, has taken a look at this problem. And all the previous work on disequilibrium chemistry just picks one reaction and then simplifies the whole process to looking at one. And what he's done is looked at the entire network, all these reactions, backwards and forwards, and we find a different result than people have commonly gotten in the past for disequilibrium chemistry for the methane at low temperature, at low gravity, and may explain why we're missing the methane in the low gravity objects. So come by and see our poster.
I'm Ty Robinson, an MPP fellow at NASA Ames. We've been hearing this morning about the connections between brown dwarf variability and clouds. Hand in hand with that, with cloud evolution is going to be thermal perturbations introduced by those clouds and other physical processes into the atmosphere. And those thermal perturbations can then propagate upwards or downwards through the atmosphere, leading to temperature fluctuations and brightness variations. So along with Mark Marley, we used a 1D model to investigate the time-dependent behavior of a model T-dwarf atmosphere to perturbations introduced into the atmosphere, periodic perturbations. This is a case where you're seeing brightness fluctuations over the course of a full cycle in the near infrared, where the perturbation was introduced at depth for a characteristic period of 100 hours. So if you want to talk about this result or similar results and the role that clouds might play, please see my poster number 324.
Hi, my name is Kev Stark. I'm from the University of St Andrews in sunny Scotland. We've long been advocates of electrostatics, ionisation processes in atmospheres, so we're basically trying to look at a process to give us patchy cloud cover. So we have atmospheric plasma, cloud particle becomes charged, electrostatic stress breaks the charged particle up into smaller pieces, and so it truncates our distribution function of particle sizes, giving us contrasting cloud properties, which could be the underlying cause for patchy cloud cover. Thank you.
Very fast. So the reason I believe they were called sparkler sessions originally is because you were supposed to do the talk in the time it took for a sparkler to burn down. But health and safety wouldn't let me have a sparkler, but fortunately, there's an app for that. So if you go to the other poster, the other sprinkler session room over in the other building, and fight your way past the orcs to the darkest part of the back of the cave there, you will find, disguised as a poster about the funnel web survey, some results from the Magellan Parallax program. We've been observing we've got results for about 17 objects, half T9, T9.5, half of them are white dwarfs. The Y0 dwarfs, contrary to what Trent and Adam told us last year in science, actually have enormous amounts of scatter in them. What else did I want to say? Oh, a Y0855 is fainter.
Hi, my name is Hao. So we present the first HSD spectral time series of L dwarf, which is a plot on the left, showing that during one HSD visit, the spectral variation between the brightest and faintest spectra of L dwarf behave differently from an L dwarf and a T dwarf, showing that the water band variability behavior is different. So we think that is a result of the relative location where the clouds are. So I think water band variability could be a proxy to detect where the cloud height in atmospheres. Thank you.
I'm Stephanie Douglas. I'm a grad student at Columbia University and AMNH. My poster's invisible. So my poster, which is number 170, is When Good Fits Go Wrong, talking about our preliminary results from fitting 2 synthetic spectra grids to low resolution data, looking at what happens if you fit band by band, and comparing the results from a couple different models. So come check it out, poster 170, and I'll tweet out the Figshare link in a minute.
I'm Caitlin Allers from Bucknell University. I also have an invisible poster. So last fall, our group reported the discovery of this cool object called PSOJ318, incredibly red, and based on its spectrum, looks young, and based on its parallax and proper motion, was a candidate member of Beta Pic. Well, we now have a radial velocity. You have to come by my poster to see if we confirm that membership.
Okay, thank you very much, everyone. So now I'm going to introduce Jacqueline Radigan, who's going to lead the second session.
Okay, so I think we're going to switch from primarily observational to the theoretical side now. Well, I guess we had. Oh no.
No.
Whoops. Scratch that. Anyway, Mark is going to start us off with a theory talk at least. I'm sure it's going to be wonderful, so I'm just going to stop talking now.
Thanks, Jackie. So I'm going to be speaking today as kind of an inside baseball talk directly to the brown dwarf community. So those of you who are here for the entertainment value, you just have to sit tight until we get to the next talk. And what I want to do is give kind of an opinion talk today, and I really want to start a discussion of what I think, because we're also nice. It's such a great, nice community, and I think sometimes that may get in the way of, except for the occasional, anonymous review, we don't always, say all the things that really need to be said. So I'm going to try and do that today, and review and critique the body of cloud models, and think of it in the context of tough love, in the sense we're trying to everybody get better, including, we need to get better, everybody needs to get better. It's time to move on. I have some suggestions for a path forward, and I'm not claiming that I know the right solution. I'm just saying we have a problem. And our problem is we have all these balkanized cloud models. Everybody has their favorite model. They all have different drawbacks. Every group has a model, and they fit data to, they go get a spectra and they fit it to a model and say this object is 1600 degrees and it's a gravity of this and it has a cloud parameter of that, and that's it. And the spectra usually don't match perfectly, and we never really find out why they don't match perfectly or what could we do better to make them match perfectly. And we also don't know why. There's not a lot of discussion of, well, why is it this way or why is it that way? And I think we're kind of stuck, in my opinion. I think we're kind of stuck, and we need to try something different. And so that's what the talk about I'm trying to get to today. So we all know there's a lot of different cloud modeling schools, and I don't think we have them all here. There's Christian Helling, where we start at the top, and we maybe particles fall down, they get bigger. There's fixed clouds where we say, well, let's imagine a cloud is one scale height and it has some particle size. There's chemical equilibrium clouds. There's R clouds. Everybody has a different approach. So I want to try to look at each of these really quickly in the whatever 10 minutes I have left. And remember, this is tough love, so don't shoot the messenger. Let's start with Cod dusting. This was a great place to start. These were two limiting cases: no clouds at all, or chemical equilibrium clouds. This helped demonstrate the importance of clouds. I think historically, when the history of this field gets written, these models played an important role. They're widely used. A lot of people have used them. They've made a great contribution. But they're horribly outdated. We understand the clouds form in layers. The dusty models assume you're in chemical equilibrium all the way through the atmosphere. When you get cold, you get more and more and more dust all the way through the atmosphere. The limit of this is a black body. You're just looking at dirt. And you'll hardly ever see fits 1,200 degrees for dusty models because they're just way too dusty. And so the fits to the dusty models always have to move up in temperature, like 1,400, 1,600 Kelvin. And then there's a luminosity problem because you're trying to fit something that's really 1,200 degrees with a 1,600 degree model. It looks too hot. And I think we need to move on from these. And certainly, in the limit of Jupiter is not explained by a dusty model. It's in chemical equilibrium all the way through the atmosphere. There's cloud layers. So at some point, it has to fail. And we don't really know where that is. And I think we just need to move on from these. Christiane Helling's models. She understands more about dust than anybody. She's thought very carefully about it. This is a reaction list you can't read of everything she includes in those dust models. I think it's great. She looks for steady state dynamical solution, all the different feedbacks. I think she's convinced everybody, me included, condensation is complicated. There's probably dirty dust grains. It's a really difficult problem. But again, it's the most complicated cloud modeling approach. It's difficult to incorporate these into forward models. When you have a mismatch, if you have 15 or 16 different species of dust, well, which thing do you have wrong? Okay, which cloud layer is wrong? Which particle sizes are wrong? It's really hard to get a handle, I think, on what's going on. And something that's not said enough is that those models depend on there being updrafts that go all the way through the atmosphere to deliver seeds to the top of the atmosphere that then fall down. I don't think I've never been personally convinced that those TiO2 seeds really exist. They really go through you really have super narrow updrafts that deliver these to the top of the atmosphere. And I think we have to recognize that's a drawback to this approach. This would not work for Jupiter. It does not explain the LT transition, and I think we have to look at that. Settle. It utilizes results of dynamical studies and a nice feedback, a nice interplay with the dynamic models. I think that's great. It accounts for sedimentation. Qualitatively produces the LT transition, and I'm looking forward to seeing the poster. We'll hear more about this today. They're widely available. They're online. People use them. I think it's great. But I don't know how they work. I don't think we've ever seen an adequate documentation for how the settle models really work. They can't be independently used or checked by other groups. There's no tunable, they frequently say there's no tunable parameters, but then what is it we're learning? What accounts for the spread and colors of the L-dwarfs? Really, what is producing the LT transition? What is it about the model that's actually doing that? What accounts for deviations between the models and the atmospheric dynamics? I mean, between the models and the spectra, we don't know. Well, what about prescribed models? These are very appealing because you say, well, I'm just going to say I have a scale height thick models, I have 10 micron particles, maybe just a few different compositions. I can vary the size of the particles and see which fits best. These early on, Suji, and we have a paper early on too that showed that layers are important. It's probably layers that are producing the LT transition, although a single layer just slowly sinking changes color too slowly. I think these kinds of models give some physical insight to what's going on. But it's really hard to tell how unique these solutions are. What if I had a thicker cloud and smaller particles, or I added a couple more species? it doesn't really tell us, it doesn't give a good handle for all the possible things that can be going on, and it doesn't really relate to the atmosphere. It doesn't relate back to the vertical mixing, it doesn't relate back to the chemistry. And so, yes, I think it's valuable for giving some insight, but it's not the final solution. And again, there's no follow-up. You know, if you have a 50 micron cloud fits best, well, why is that? Where are those 50 micron particles coming from? And so because of that, I don't think they have a lot of predictive power. So last but not least, what about our models? I like to think they're well documented. There was an Ackerman and Marley paper. They were developed by Andy Ackerman, who spends his life modeling clouds. He has a great insight into what's important, sedimentation, particle growth. It works well over a reasonably large range of parameter space. I think it's really demonstrated that clouds are in finite layers all the way through the LT sequence. Caroline has shown you can apply them to a brand new set of parameter space, the cold clouds, where they still work reasonably well. I think it's been a useful framework. But they're not widely used. Nobody else uses them other than us. There's been no physical follow-up. We fit a lot of papers in. Well, we fit these spectra with F set equals 2. But why is it F set equals 2? What is physically causing this type of cloud? And nobody, including us, has really looked at that. There's other tunable parameters that don't get mentioned a lot, or how exactly we treat the eddy mixing. Those really haven't been explored. We assume pure grain compositions. We have clouds of distinct compositional layers. And certainly what Christiana's shown is that's probably not true, but that's what we do. And we've lately been adding things. We've added holes. I think it helps. But Clayton Curry calls them epicycles. And I'll take that criticism. I think that we're adding things to try to get better, but is that really physical? Is that really the right way to go? So what are we going to do? And I think we need, as a community, to move on to a new generation of models. I think we need a physically based forward model. Ideally, it would be open source. It would allow us to explore a diverse set of influences, document better exactly how these things work, bring more ideas, fresher ideas into the problem of how to approach this, and hopefully move beyond just fitting of spectra, models of spectra, to better understanding. My contribution, the eddy set model, we call it eddy set, the Ackerman and Marley model. Andy wrote it. It's pretty well documented. It has the physics module, but it also has a lot of bookkeeping that's really a pain in the butt to create from scratch. If somebody could go in there, if they wanted to, and change the physics, do some kind of different cloud approach, it wouldn't be that hard. So I'm going to make EddySet open source. When I get back and have some time, I'll post it. Let anybody that wants to use it. You don't have to use it to somebody else entirely. But just as a step forward in trying to get more ideas out there. And hopefully other people will join us and make these things more publicly available so we can try to get a clearer handle on what's going on. So in conclusion, I think we all need to better explore model mismatches. Why doesn't models fit the data? What's going on? Use multiple cloud models. Try to understand physically what's going on. I really think we need to stop reporting fits to Conn and Dusty. It's just, I think we need to move on from that. Maybe the real future is inversions. I encourage you to listen to Mike Lyne's talk on Wednesday morning, where he's inverting for temperature profiles and abundances, and in the future, hopefully cloud properties for brown dwarfs. So just take the spectra and see what the spectra is teaching us. But I'm hoping we can discuss this, get more ideas, and as a community, see where else we can go. I'll stop there. Thank you.
Okay, so we have plenty of time for questions. So Adam? Showman? Oh.
Hi, that was really interesting. Some of the comments you made about, like, let's say the term you used, but for the direct models, like the ones where you assume a set particle size, or in your case, say with FSED, one of the weaknesses you alluded to was basically it's just a one-off. Assume 50 micron particles for some cloud, and there hasn't been an answering or an addressing of why and an exploration of parameter space. That latter issue about whether the parameter space is explored is not in and of itself a defect of that approach. It's more just how does one go about, to what extent is a given person interested in sort of exploring the parameter space. I mean, that couldn't happen here too if one has a new cloud model. I was curious to get your take on that. I don't really understand why that hasn't been happening. I don't know if you have a comment on that.
I think because it's hard to imagine all the possibilities. I mean, there's thick clouds, thin clouds, there's different particle size. Do you vary the number density vertically through the clouds? And I think it's just been a little intimidating for people, and they've maybe come up with 4 or 5 solutions, then go do a bunch of fits and say, well, these fit pretty good. And it seems to stop there. Maybe a different approach could be to a much bigger grid, or try to be a bigger set of imagination for how you might parameterize the clouds. But the people that use those more, Adam Burrows' group, for example, might have a better handle on exactly why they haven't explored more. But they have maybe 5 or 6 different flavors of clouds they've looked at.
Well, since you're already standing, sorry, do you have a question, or you're just
No.
asking us? Great.
You get to decide.
Ken, why don't you go ahead?
But so as an observer, I'm mostly interested in the models so that I can invert some spectrum I observe and get some properties out. And one of the things I sometimes feel a little hopeless about is as we understand more, we realize we need to, there's clouds that operate differently at different parts of parameter space, and need to add more knobs. And are we going to add so many knobs in the end that it'll be impossible to actually invert things when we actually understand things correctly?
Well, that's the concern. Is what's the right number of what's
needs to be degenerate.
Just Kelly is looking at that.
If you do say have $1 million in your model, you do like M state, for instance, you will naturally explore your parameter space. And let's say you have a parameter that just doesn't matter. You'll get out what you put in. You won't get a constraint on it. And that tells you, the Bayesian way sort of tells you that you didn't constrain that particular variable. So it's kind of, you sort of think, I don't want to put 1 million models or parameters in my model, but you can in some sense, because you just won't get any constraints on the ones that don't matter. Or you could do it a more sophisticated way where you actually do sort of Bayesian hypothesis testing, one of my significance of a particular physical parameter. So there's a gazillion ways you can do it.
And I think the bottom line is that there's, and we've time for another question. You have many parameters, right?
Yeah.
Yes. And so it prevents that over
Another thing that MCMC or Bayesian things will let you do is if you have extra parameters that you don't care about, you can just integrate over them and get a result irrespective of your other model parameters. You can get temperature no matter what the fits in the other parameters were.
I'll say 2 tough love things. The first is, in the Bayesian sense, MCMC is great, but if you build the wrong knobs, it doesn't matter. Forget about it. And the second comment actually is tough love to you, Mark, actually specifically. Since none of your, a small number of your theorist colleagues are here to shoot at you, I'll shoot as an observer.
That's why I gave you the talk.
Exactly. Yeah, I didn't want this. So, we have thousands of spectra. We have, hundreds of objects with distances. We have 100 objects with ages. We've got dozens of objects with dynamical masses. We've got a dozen objects now with super precise time variable, monitoring what they do. So from my perspective, we're not hurting on that end. We're not hurting on the observation. We're not hurting on the tools to do the analysis. One of the things I think we are hurting on is just bandwidth from the theorists, right? You've listed 5 groups, and that's 5 of you or 10 of you or something. But how do we observers, we have many desires. How do we help you produce, the things that we want, and also the bandwidth to work on these problems?
Say nice things about our proposals. I mean, we need a division for variability, and we don't have one. So people are scheming all this great variability stuff, and they're asking us for models, and I don't have enough personal time. And the members of our group, we're all trying to do something, but we just need more people to move this forward. And postdocs, come to Ames.
Okay, great. And I think on that note, let's thank Mark and welcome. Okay, next up we have Kay Hiranaka, and she's going to tell us about her work modeling hazes in Dwarfs. I think.
Okay. Good afternoon, everyone. My name is Hiranaka. I'm a last year grad student at Hunter College and the American Museum of Natural History. And I'm working with Kelly Cruz and Mark Marley, and I'm going to talk about the dust haze of small particles in young Dwarf atmospheres. So young dwarfs are redder than field dwarfs. So this is from Fatty et al. 2013. The gray dots are field dwarfs, and the red circles are young dwarfs. So young dwarfs are redder than the field dwarfs. And young dwarf spectra look different from field dwarf spectra. So here is a normalized flux versus wavelength, and the red is a L0 gamma, and the black is the L0 standard. And the field dwarfs have clouds in their atmospheres, but we hypothesize that the young dwarfs have an additional dust haze of small particles in their atmospheres that causes the observed reddening. So Morocco et al. 2013 did a very similar analysis, but we did things differently. So here we're assuming that the field and young dwarfs are identical except for the dust haze. So we want to isolate the effect of the dust haze. So we take the simple basic radiative transfer equation. So the flux of the young dwarf is equal to the flux of the field dwarf times e to the negative tau, which is the optical depth due to the dust haze. So if you take the ratio, if you divide the field dwarf flux by the young dwarf flux, we get the additional opacity due to the dust haze. Okay. And the additional opacity, the observed reddening, looks something like this. So this is the field dwarf flux divided by the young dwarf flux, and we're not concerned about the gravity sensitive features here. We only care about the overall shape, which is in the green dot, that we hypothesize is caused by the dust haze. Okay. So we're trying to parameterize the dust haze by using a Hansen particle size distribution. So this plot is the number of particles per volume as a function of radius, and the gray lines are two power law distributions that are widely used to describe particle size distributions. So we used the power law distributions at first, but the results didn't reproduce the observed reddening. So we needed another particle size distribution. And the magenta shows a Gaussian distribution that's described by Morocco. And in green are Hansen distribution. So the Hansen distribution, it describes the water droplets in the clouds of Earth that might also reflect the cloud formation in brown dwarf atmospheres. So the Hansen distribution has two parameters. A is the mean effective radius, and B is the effective variance. And here I'm showing two Hansen distributions with the same mean effective radius, but different effective variances. The solid line has a wider variance, and the dashed line has a smaller variance. So with a smaller variance, the Hansen distribution looks similar to the Gaussian, but it's wider than the Gaussian distribution. Okay. So we use the Hansen distribution and mean theory to constrain the particles, the dust haze properties. So this plot shows the extinction coefficients for dry grains, which we used for as scattering particles. And Morocco et al. Used other grains. They used ancetite and corundum and iron, but they're all supposed to exist in brown dwarf atmospheres. So it shows extinction curves for straight grains as a function of wavelength according to the Mie theory. And from this plot, we can visually conclude that the small particles reproduce the observed reddening. This shape for the small particles resembles the observed reddening. So to put a tighter constraint on the Hansen distribution parameters, we use MCMC. And this is my particle size, the probability distributions. So this shows the probability distributions for my MCMC parameters. Log S is another parameter added to provide tolerance, but A and B are the physical parameters that we care about. And from this distribution, we can constrain the Hansen grain size distribution parameters. And this MCMC result looks like this. So the black is the same observed reddening that I showed a few slides ago, and the green is the MCMC result, and the green line fits the observed reddening beautifully. So the dust haze can explain the observed reddening. So I applied this method to 25 low gravity objects from Cruz 2009, and this is the results. So this is radius versus spectral type, and everything is small. Many of them are under 0.15 micron. And another thing here is that for L4 and L5, L4 and L5 might have different populations of grains. They might have populations of slightly larger grains than from L0 to L3. Now I also plotted the radius against J-K color, and here you can see the correlation. So the redder objects have bigger grains in their dust haze. So my conclusion is that population of small grains can explain the red acidity of young L-dwarfs, the population of small grains that does not that's not in the current models. And Hansen grain size distribution can explain the observed reddening as opposed to Gaussian or Power law. And my future work includes applying this method to other red objects, like red older L-dwarfs, and incorporating different grain species. Thank you very much.
Thank you, Kate, for being perfectly on time.
Caitlin? So Kay, you're making, when you're looking at the effective dust, you're comparing objects of the same spectral type,
yes,
a young and an old.
Yes.
What if they're not the same effective temperature?
Well, we're assuming that they are.
Well, one of the things that we have found with some young L-dwarfs is that they have a lower effective temperature than a field dwarf of this, a normal field dwarf of the same spectral type.
Okay, that's something we should look into more carefully.
John?
So could you comment about what your method predicts for the so-called optical spectral types, sort of in the 0.6, 0.7, 0.8 micron range, or is that sort of not under consideration?
That's beyond the scope of thought right now.
Okay, one more fast question, then we need to move on.
So first saying that your conclusion make a lot of sense. So that the density is redder because they are small particles make a lot of sense because the gravity is supposed to be lower. So then the particles be kind of staying in the upper atmosphere. And I have another question. Did you compare this spectra with other Young-Brondorf spectra?
So comparing young to young, I haven't done that. I've only compared young objects to field objects.
Okay. And didn't you measure the equivalent widths of the alkaline lines?
I don't know about that.
Okay. Okay, because well, if you measure these equivalent widths and compare with other objects, you can see actually how young, if it's young, how young it is, because the equivalent width should be much lower. But it's okay. Thank you.
Okay, let's thank Kay again. So next up we have Will Best, and he's going to be talking to us about LT transition dwarfs in pan-stars.
Okay, how's that? All right. Good afternoon. Thanks everyone for coming, and thank you to the organizers. I'm going to shift gears here significantly. This is the talk that means we can't just talk about theory in this section. I'm going to tell you about a search for LT transition dwarfs that I've been leading that's wrapping up now. Large-scale search, and of course, why are we interested in these objects? Well, we've heard a lot about them today already. There's these significant changes in the photospheres that happen. You can see the spectral changes here. And it's over a fairly narrow temperature range. And you also get this blueward shift in the near-infrared colors as objects move through the LT transition. Obviously, these have been well targeted for variability. We want to understand, though, the evolution all the way through this sequence. And along with doing the studies of individual objects, which give us these very important snapshots in time, we also need to study large samples at a range of different temperatures so we can map out the whole evolution through the LT transition all the way to late T-types. So a challenge we've had is that we know of relatively few LT transition objects. So there's the cloudy clearing glare. We know of relatively few of these objects. This is a census as of January of this year, and you can see relatively few LT transition objects compared to the earlier and later types. There's a couple effects in play here. One is the narrow temperature range, so objects evolve through these spectral types more rapidly. So we'd expect somewhat fewer of them. But there is a selection effect. Most of the large searches that have been done for brown dwarfs have not been very sensitive to the LT transition. The big reason for that is the near-infrared colors. These objects are brightest in the near-infrared, but compared to other earlier spectral types, particularly late M and early L, the colors are almost exactly the same. There's a lot more early L and late M objects, and they're brighter, so you can see them further away. So sifting out the LT transition is real needle in a haystack kind of work here. In the mid-infrared, you can do somewhat better. This is the Y's W1 minus W2 color. Of course, it's spectacularly good at finding later objects. If you make a cut for the LT transition, you can find the early T's, but late L, these purple and green points, have the same colors as many background objects as well. So the new tool that we brought to this game is pan-stars, which is also an optical survey. I should mention there have been a couple successful ones previously, in particular Sloan and one using UKIDS, but they were focused on smaller areas of the sky. Pan-stars is wide field, 30,000 square degrees. It's optical like Sloan, but about a magnitude deeper. And it has a Y band at about 1 micron that makes it much more sensitive to ultra-cool dwarfs. So we've taken tools that were developed for pan-stars and merged the catalog from the pan-stars 3Pi survey with the Y's all-sky results. We have this massive database, 30 billion objects, and we use the pan-stars tools to search through it in the standard way with photometric criteria. So these are the two main colors that we use. There's the W1 minus W2, very familiar from Y's, and also the Y from pan-stars minus W1. I'm taking you through this plot. The big black cloud down there in the left-hand corner is 50,000 M dwarfs from Sloan. And then the sequence going to later type objects goes to the right through the late L's and then swings up to the left as you go to the cooler T dwarfs. And you can see that the Y minus W1 color is doing a great job of spreading the L dwarfs, especially the late ones, out from the background objects. That's what we needed. That's how we get around the color confusion and focus specifically
on the LT transition objects. So we use these photometric cuts, a couple of other ones as well. We also used a cut I'll talk about in a second, trying to select nearby objects to have a volume limited survey. We inspected a lot of images and eventually got near-infrared spectra with specs on IRTF. So here are some initial discoveries published last year, 7 very bright objects within 15 parsecs. We've of course carried on. By now we have 80 LT transition dwarfs, so pick your favorite one out here. And summarizing the results, we've obtained over 140 spectra. More than half of them are LT transition dwarfs, so we've been very successful at finding them. And the blue histogram here I'll say a little bit about. I mentioned we wanted to be volume limited, but it's tough to do that when you don't have parallaxes and not even spectra yet. But after some experimentation, we found that the W1 and W2 photometry allowed us to select objects that are within 25 parsecs fairly accurately based on objects where we already had parallaxes. So we made a specific cut using W1 and W2. Objects passing that cut are in blue, and the ones that have spectrophotometric distances within 25 parsecs are in red. So we're doing pretty well there. There are a total of 28 objects within spectral types L6 to T3.5. Here they are compared to all the known ones, including our discoveries. So this is the contribution that we've made. Now, what are we doing to try to understand the LT transition better now that we have data in hand? One thing we focused on is motivated by the Soman and Marley hybrid model, so one other group at least using this model. So in this color magnitude diagram, the green points are modeled objects and the other colors are objects with known parallaxes at the time. And I want to focus specifically on the middle of the transition, where there's this pile-up, relative pile-up of objects there, which in the model is explained by a release of entropy as clouds clear, as they do in the transition. And that release of entropy slows down the evolution. So you kind of get a piling up of objects there. Now, is this a real feature? Well, in 2012, Dupuy and Liu published their large compilation of objects with parallaxes, and here's the CMD from that. And there kind of is a suggestion of the pile-up there in the middle, along with, right after it, a suggestion of a gap, which would indicate some kind of very short-lived phase in the evolution, because there are just not very many objects there. So this was objects all with parallaxes, but not volume limited. We've taken our sample now and included it in a sort of pseudo-volume limited sample where we're using whatever distance is available, photometric or parallax if you have it, to create a volume limited set. Oh, sorry. I should show one more plot first. This is from Dupuy and Liu. They focused on the LT transition and computed this distribution of colors in a Monte Carlo fashion that incorporates the errors. And you can see in there pretty clearly there's this gap, and then right before it, there's the pileup. And they had 36 objects in their sample. So in our new pseudo-volume limited sample, we've got 62 objects. We still see the gap, so it's becoming an increasingly real feature. And we also have this suggestion of a pileup, and maybe of possibly more structure as objects enter and proceed through the LT transition. Now this is, again, this is selected with a lot of photometric distances. What we really want is a true volume limited sample. So that's what I'm going to be working on building for the next couple of years. A very large sample, spectral types now covering L0 through T6, out to 25 parsecs, covering about 2/3 of the sky. In the end, it should have around 400 objects, so that should definitely be large enough to do great analysis. Not all in the LT transition, of course. But it will be defined by parallaxes, so we'll be getting parallaxes for about 300 new objects using pan-stars and in the near-infrared with UCURT. This should be a really nice complement to the work that's already been done by recons with earlier type objects and the data that will come from Gaia in the next few years. And that's it. Take questions.
Will, can you quantify at all on that distribution of color, probability distribution, what the uncertainty is per bit error?
I haven't run a quantification of that. I would say in general, The color uncertainty for a particular object is about 50 millimags, typically. I would be guessing at this point, so yeah, sorry.
So I guess one of the most interesting results, that are out there is that the Sloan selected objects have different colors on average than, two mass selected objects. And I think it'll be really important, as your sample develops and the sort of competitors hopefully, find other, holes in your selection criterion, to find out, what the true color distribution of these things are. Because I'm very worried that there's selection effects, correlated with metallicity and gravity and all kinds of parameters out there that we don't really know about. So I'll just put that out there for encouraging you to publish quick.
Yeah,
really your sample.
Yeah, the volume limited sample is the only way to get around that. Making sure that it really is volume limited and we haven't missed some strange color selection effect that'll be key.
Is there any other questions? Okay.
My poster is 131 if you want to see this again.
All right, let's think well. And finally, to end this session, Caroline Morley is going to tell us about clouds and the coolest ground dwarfs.
Okay, so wait, Adam, did you say I have 12 minutes? Oh, that's awesome. Okay, I can talk slower than I was planning on talking. Okay, so I'm going to jump right in here to this plot. So this plot was shown earlier by Jackie Radigan. So this is from her latest paper. So what I want to get across here is that a number of brown dwarfs, as we've seen this morning, have been observed to be variable outside of the canonical LT transition, right? So even though your eyes to this plot are immediately drawn to the center where these really high amplitude variables are, I'm actually most interested in these objects down here in the T-dwarfs that exhibit variability even though we don't believe there's any sort of dramatic change in cloud cover happening at these effective temperatures. So these are what I'm going to focus on for this talk. These ones and then cooler ones which we're starting to see are also variable. Okay, so what I've done here in this recent AppJ letter, which was posted on the archive this past week, is divide the things that can cause variability, physical processes, into two categories. So the first of those is patchy opacity sources in your atmosphere. So the idea here is that you have a brown dwarf and one side is more covered in clouds than the other side. So you have more holes or more thin clouds on one side of your object than the other. As it rotates, you'll see variability, spectral variability, as the cloudier side rotates in and out of view. The other category of causes of variability are changes to your actual pressure temperature profile of your objects. So you can imagine dynamical effects that are happening in your atmosphere that are causing parcels of air to rise or sink and cause them to be warmer or colder than you might expect. And you can also imagine that these things are actually coupled, right? So you have some underlying cloud layer and it's actually radiatively interacting with the atmosphere above it and warming or cooling parts of the pressure temperature profile. So what we're going to do here is investigate these two different causes of variability and see if we can actually disentangle the spectral variability that we expect to see from these. Okay, so I'll start with the patchy clouds. So since I'm focusing on the T-dwarfs and the Y-dwarfs, I'm including clouds that form in cool objects. So here we have pressure temperature profiles of objects that span the T-dwarfs down to kind of warmer Y-dwarfs and condensation curves. So where each of these pressure temperature profiles meets the condensation curve for that particular material, you'll form a cloud. So you're used to thinking about the clouds over here. These are the L-dwarf clouds, iron, silicates, things like that. But I'm actually focusing on these sulfide and salt clouds. Things like sodium sulfide and potassium chloride are important. And then for the coolest objects, we actually condense water clouds in the atmosphere. We've run a whole grid now of models that include those water ice clouds for the Y-dwarfs. And we find that they're pretty important, especially once you get to the really cold Y-dwarfs. So what we're doing here that's different from our normal models is running patchy clouds. So these were first implemented in Marley et al. 2010 to reproduce the LT transition. We also used them to converge water ice cloud models in our paper earlier this year. So briefly what we're doing here, we're calculating the flux through a clear column and a cloudy column of our atmosphere. Then we add up that flux in order to calculate the pressure temperature profile of our object and the average spectrum that's coming out of our object. So we're summing this flux to get the temperature structure and the spectrum of the object. And then what we do is assume that even though our object is overall 50% cloudy, so all of these will be total 50% cloudy, these aren't uniformly distributed, because to get variability, we need more clouds on one side of the object than on the other side of the object. So when we do that, so this is 50% cloudy total, but we have 30% cloudy on one hemisphere, 70% cloudy on the other hemisphere. This is a 700 Kelvin object, so falling right in those kind of mid to late T-dwarfs. So this is what you get for the spectra. You see that in general, you have more flux coming out through the less cloudy hemisphere of your object. This is what we expect, right, because there's less opacity. And in particular, you'll notice that this effect is really focused in Y, J, and H bands. So you're seeing the highest amplitude variability within these major windows in the near-infrared between opacity sources in your atmosphere. So you can show this as a flux ratio. This is just the black line divided by the orange line here. And to get the observed variability that you would expect to see if exactly this physical process was going on in your atmosphere. And you really see the highest amplitude variability within those windows. So that's very similar qualitatively to the types of variability that we've observed at the LT transition with, for example, HST with the GRISM spectroscopy. So you can put this on a color magnitude diagram. This is a little bit different than normal color magnitude diagrams we show. So the middle dot here is the 50% cloudy converged model. And then we also show the model photometry for the clear column of our atmosphere and the cloudy column of our atmosphere. So you can see that for the T-dwarfs, you're really affected by these sulfide clouds. You see a strong color shift so you can imagine that if you were variable, you'd go kind of back and forth a little bit across this line. So you expect to see a color difference there. The shift in pattern that you see down here is due to the formation of water ice clouds. So once you start to form those water ice clouds, you actually swing the other way. You get bluer in J minus H when you have the water ice, and that's because water ice just doesn't absorb that much in J band. It mostly scatters in J band and absorbs in H band. We can show the same thing for the mid-infrared. So this is the Spitzer 3.6 minus 4.5 versus 4.5. And you can see that in these T-dwarfs, you expect to see very little variability at all due to just the patchy cloud cover in these atmospheres. You start to see variability really kick in once your water ice clouds start to become optically thick, once you hit temperatures of sort of 350 Kelvin. Okay, so that's patchy clouds. We expect to see variability within those spectral windows between absorption features. What about for hotspots? So what we're doing here is we're adding energy as we're converging our pressure temperature profile, the temperature structure of our atmosphere. As we're converging that, we're adding energy at specified levels of the atmosphere, all the way from the top of the atmosphere at 0.1 bars down to really deep within kind of the convective part of the atmosphere at 30 bars. So you can see that actually changes the temperature structure of your brown dwarf a lot. And these are all run such that you end up with 1.5 times the amount of flux coming out through that hotspot spectrum than through the what I'll call the baseline spectrum in these models. So what does that look like in the spectra that actually emerge from these objects? So this is again a 700 Kelvin object, and you can see that just looking at the spectra, it really doesn't look that different. But when you dive in and look at the flux ratio, so the baseline model here divided by each of the heated models, then you see that you actually get really significant variability within the absorption features themselves in the atmosphere. So here, for example, at this 3.3 micron methane feature in the atmosphere, you see really substantial variability when you're heating really high up in the atmosphere where that flux is actually coming from. So this is, of course, a completely different pattern of variability than we saw for those patchy clouds. So this is really promising, right, because it means that if there are temperature perturbations that are happening and maybe propagating through our atmosphere in complicated ways, we can maybe disentangle it. It seems really likely that we'll be able to disentangle that type of thing from patchy clouds in the atmosphere, even if they're both happening at the same time. And again, we can put these on color magnitude diagrams to see how this is different for different temperatures. So the baseline model is here, and then heating at different levels is shown as the colored points. So you can see that in the near infrared, you change the most in color when you're heating kind of in the middle of the atmosphere, right where your near infrared photosphere is. So that makes sense. And if you heat really deep in the atmosphere, you kind of just you look like a slightly warmer version of yourself because you're heating the whole pressure temperature profile. What's really dramatic, though, is the difference between the patchy clouds and the hot spots if you look in the mid-infrared. So you can see here that with this sort of substantial heating at 0.1 bar, you change your 3.6 micron flux a really significant amount. So if we're seeing variability at 3.6 microns for these T-dwarfs, I think it's really likely that it's due to temperature perturbations high up in our atmosphere rather than patchy cloud cover in our atmosphere. Okay, so I'll conclude here. We found that the two different paradigms of variability will have really different spectral effects. So I think there's really strong potential here to be able to retrieve what's actually going on in mid-T and wide dwarf atmospheres. And I'd also like to advertise briefly that models are now available for all of our cloudy T and wide dwarf spectra and photometry, including all of our 400 Kelvin and cooler objects that have the water ice clouds. So if you go to my website, which is listed there, you can download the spectra and the models. There are links there to the evolution models as well. So hopefully those are really useful for the community. Thank you very much.
Hi. I was wondering, as a variant on the patchy cloud model, instead of having, say, a variation in the fraction of patchiness from one side of the object to the other, if you kept the patchiness fraction the same, but let the cloudy regions optical depth vary. So, for instance, instead of on one side having 70% holes, still have 50% holes, but the cloudy regions have an optical depth of half instead of 2 or whatever. Does that produce different signatures than what you've described? Or, in other words, is it degenerate, or does that produce a signature that you could distinguish from these two cases, considering that as a third case in a sense?
Yeah, I'd have to actually think about that and run the models for it. I think a lot of these things are going to be pretty degenerate, that you can have different sort of sets of clouds and holes, or thin and thick clouds that can reproduce the observations that we see. But I think you'll definitely see a difference if you don't actually have, say, holes in the clouds, as has been suggested. You have thin clouds instead and kind of vary the thickness there. I think that would actually look different in terms of the ratio between flux and, say, J and K bands, things like that. So I'm not sure. I'd have to run some models. It's a good question.
Hi, Carolyn. Here's a wacky question.
Yes.
Could you envision a day where, as this sort of modeling becomes more mature, in fact, we might actually use the properties of variability, the timescales, the amplitudes, the wavelength dependence, as an independent temperature determination for the object, as opposed to now, temperature comes first, and then the variability modeling comes on top of that?
You want to use variability and the things that it tells us.
Well, the way we measure temperature now is we use the Stefan Boltzmann model, we fit some models for a single epoch. Could we actually have a day where particular phenomena only occur in variability space as a function of temperature, and we could actually use that as a temperature probe? Is that crazy?
I don't think that's ever going to work. But given the scatter and variability properties that we see as a function of effective temperature, I think that's going to give us more scatter than the methods that we're currently using to calculate luminosity.
Wouldn't you need to get models that actually agree with the spectra first?
Sure. Yeah, but I think
third likely one.
Yeah, and I mean, I think we can really start to learn a lot about the physics that is happening in our atmosphere, sort of the sizes of circulation cells and things like that are happening on our objects as a function of rotational period and things like that should really affect the dynamics. So I think there's a lot of physics that's wrapped up in the variability stuff that is really going to start to come out as theorists dive into the really nice data that all of the observers have given us.
Okay, I think we're out of time for questions, but I'm sure. Okay, so now we're starting session 3 of our program, which has one speaker, and David Singh is going to tell us how all of the clouds we've been talking about connect in the exoplanet regime.
Hello, so thank you very much for giving me the opportunity to speak to you today. Yes, I'm going to shift things a lot from brown dwarfs to exosolar planets. So I I thought it was kind of funny. I'd see we have thousands of brown dwarf spectra, and you're going to see a few exoplanet spectra. So we're in a completely different regime. This is kind of the Wild West, but there is quite a bit of overlap, I think, going forward, especially with clouds and hazes. No variability yet. Variability scares me, but I just want to quickly acknowledge a lot of my colleagues and collaborators that are working with me on this data, especially the large HHC program. So I'll quickly outline just, essentially I'm looking at transiting planets, how we use these to actually study the atmosphere of these planets. And clouds is becoming a really reoccurring theme, both in small planets and big planets. And so I'll talk a little bit about the big planets, 1A9733b, and some of the results from the large program. Okay, so hopefully everyone knows what a transiting planet is. Those are planets that pass in front of their host star as viewed from the Earth. And we can use these to get spectra out. So how do we do this? Well, as a planet transits, the light filters through the atmosphere and it leaves a spectral imprint. So at wavelengths where atoms and molecules absorb high in the atmosphere, you can measure the radius of the planet, and that will be larger at those wavelengths. And so the trick is then to gather a whole bunch of transits at different wavelengths, and you measure the different radii, and you then build up what's called a transmission spectrum. And you can also think of this as an absorption spectrum, and it's very sensitive to atmospheric composition. And you can play the other trick while the planet goes behind the star during the secondary eclipse, and during this event, you could very effectively subtract out the light of the star from the light of the planet and separate them, and you're left with just the flux of the planet itself. And if you're in the near infrared, then you can play this game, take many different secondary eclipses and many different wavelengths, and you build up an emission spectrum. This is much closer to the sort of spectrum you're used to in astrophysical context. And if instead you're looking in the optical, you can actually start to get some albedo data and look at the reflected light from these planets. So with transits and eclipses, we can actually start to get fairly good constraints, good in exoplanet Earth sense, not brown dwarf sense, on the atmosphere of these planets. Now, this year already, it's not even over yet, but has been pretty remarkable for the spectrum of smaller, cooler planets. And there's this recurring theme of clouds. And so the sort of transformational one is because we have more small planets to look at, and then the new capabilities with Hubble means that we're starting to get spectrum. And you see here it's 4 cases, 4 different planets, and in each one there's the model spectrum, which should be in the near infrared sort of carved out by water, people the model show, but we have sort of frustratingly flat spectrum in each cases. And one of the main ways to do this is to have some sort of very high altitude cloud layer sort of covering all the features that you expect to see. So for the smaller, cooler planets, we have these sort of potentially have clouds that are very important. Well, for the hot Jupiters, we've had evidence of clouds and hazes actually for probably about 7 years, and this is HD 189733b. This is our best characterized transiting extrasolar planet. And there's evidence for haze in this one, so I just wanted to sort of highlight sort of the reasons why we think this is. So one is, here's the transmission spectrum, and just normal sort of cloud-free models gives you this, the bottom shape here,